Let us perform DC analysis of a common emitter amplifier. The biasing technique used in this type of common emitter amplifier is the emitter stabilized bias. The circuit diagram of the common emitter amplifier is shown on the left portion of your screen. The circuit is powered by the DC voltage source, which is VCC. There are three resistors RB, RC and RE. These three resistors form the part of biasing network. This circuit is very much similar to that of the fixed bias except one small change. An additional resistor RE is added between the emitter terminal of the BJT and the ground. The input AC signal is Vi, which is connected to the common emitter amplifier with the help of input coupling capacitor C1. The output of this amplifier is V0. This is also an AC signal. C2 is the output coupling capacitor. Another capacitor CE is added to bypass the resistor RE. This will bypass all the AC signal to the ground. So this is the circuit of common emitter amplifier that uses emitter stabilized bias. The addition of this additional resistor RE to the emitter terminal greatly increases the stability of this circuit. The goal of the DC analysis is to find the currents IB, IC and IE and different node voltages VC, VB and VE. At the end, we will also find the static power dissipation of the active device, which is BJT. So let us start performing DC analysis. Step 1 is to remove all the AC signal sources. We don't want the effect of AC signal sources on our analysis, so we will have to remove Vi and V0. We can do that by open circuiting all the capacitors. There are three capacitors, so we need to open circuit C1, open circuit C2 and also open circuit the bypass capacitor CE. Capacitors act as open circuit for all the DC signals. So after removing the AC signal sources and open circuiting all the capacitors, the circuit looks like this. Next step is to mark all the currents and different node voltages. So let me mark different currents. The current flowing through the resistor RC is the collector current. So I'll mark it as IC. This flows into the collector terminal of the BJT. The current that flows through resistor RB is the base current. This current flows into the base of the transistor. I'll mark it as IB. And the current that flows out of the emitter terminal and through the resistor RE emitter resistor is the emitter current. I'll mark it as IE. So apart from these three currents, let us also mark voltages. The voltage drop between the base terminal and the emitter terminal is VBE, and this is the polarity. If the BJT that is used here is silicon BJT, then VBE will be equal to around 0.7 volt. Then the voltage drop across the output terminals, that is collector and emitter. So this is in the output loop. So this voltage drop is equal to VCE. So we have marked all three currents IC, IB and IE and these two voltages VBE and VCE. In the next step, we will apply KVL to the input side loop and we will find the base current IB. So I'll have to apply KVL to the input side loop. We start applying KVL from VCC. Then we will move through base resistance RB. Then we will encounter the voltage drop VBE. And then we will encounter emitter resistance. And then we will encounter the ground. So this is the path in which I should apply KVL. So let me start writing the KVL expression. We start from VCC. So VCC. Next we encounter voltage drop across resistance RB. So VCC minus IB RB. Next we encounter the voltage drop VBE. So minus VBE. Then we encounter resistor RE. So voltage drop across resistor RE is RE into IE because that's the current that is flowing through the resistance RE. So IE RE equal to 0. Okay, the goal is to find the current IB. So VCC is a known quantity, VBE is a known value which is 0.7 in case of silicon transistor, RB is known, RE is also known. The only unknown quantity is IE. Of course, I'll have to find out IB, but I'll have to get rid of this term IE. So I will rewrite IE in terms of IB. That can be easily done. In a transistor, we know that IE is equal to IB plus IC. And IC can be written as beta times IB. IC is beta times IB. I can write IE in terms of IB as well. So if I take IB common, I'll get 1 plus beta times IB. So IE can be written as 1 plus beta times IB. So let me rewrite this expression. VCC minus IBRB minus VBE. I'll rewrite IE in terms of IB as 1 plus beta times IB times RE equal to 0. So I have replaced IE with 1 plus beta times IB. I'll rearrange the terms to find out what is IB. So we get VCC minus VBE minus IB, I'll take common. So what is left is RB plus 1 plus beta times RE. This equal to 0. So I'll get the expression for IB, so which is VCC minus VBE divided by RB plus 1 plus beta times RE. So this is the expression for finding out base current IB. So please note here, if RE is made equal to 0, if this RE is made equal to 0, then this circuit reduces to that of the fixed bias. And you can see in the expression as well, if you substitute RE as 0, then this second term is equal to 0, and the expression what you get for IB is same as that of the fixed bias. We found out what is IB. In the next step, we will find out what is IC. We will make use of this expression IC is equal to beta times IB, where beta is the current gain of the transistor. Easily we can find out IE also. Beta value is known, IB is found out in the previous step, so easily I can also find out IE. Or if you want to make an approximation, you can also do so. So IE will be approximately equal to IC because IB value will be much smaller compared to that of the IC. In the next step, we will find out what is VCE. So this can be done by applying KVL to the output side loop. So we will start from VCE, we will move through RC, then we encounter the voltage drop VCE, then we encounter resistor RE all the way to ground. So let me apply the KVL now. So it is VCC minus ICRC. Then we encounter the voltage drop VCE minus VCE. Then we encounter the resistor RE. So minus IE RE is equal to 0. VCE is equal to VCC minus ICRC minus IE RE. So this is the actual expression for finding out VCE, that is the voltage drop across the BJT. If we approximate IE to be equal to IC, then we can also write VCE as VCC minus IC times RC plus RE. So this is an approximation. This can also be used most of the times. So voltage drop VCE is found out. Next, we shall find out the static power dissipation of the BJT and also the other node voltages. Static power dissipation is denoted as PD, which is equal to voltage across the device. Voltage across the device is VCE and current flowing through the device is IC. Here we are assuming that IC and IE both are approximately same. IB is negligible, so current flowing into the device and current flowing out of the device is same, almost similar. So this is the static power dissipation of the transistor. Let us quickly mark the remaining node voltages. We have VBC here, the voltage between base and the collector terminals. Then we have absolute node voltages. So this node is collector node, so voltage at this node is VC. So this is measured with respect to ground. So this is the voltage that is measured with respect to ground. So this is VC. Then we have the base terminal here. So voltage at this node is VB. This is also measured with respect to the ground. So it is this voltage with respect to ground. Then we have emitter terminal here. So this is VE. Okay. So VE is measured from this point till the ground. So VCE, as you can see here, is the difference between VC and VE. So between collector and the emitter terminals, which we have found. So let us first find what is VE. In case of fixed bias, this terminal emitter is connected to the ground directly. So VE value was 0. Now this emitter terminal is not connected to the ground. We will have to find out what is VE. As you can see here, VE is also the voltage drop across the resistor RE. So VE can be calculated as IE times RE. Since we already know the value of IE, VE can be calculated. Then using double subscript notation, I can write VCE as VC minus VE. I have calculated VCE. VE is calculated in the previous step. So easily VC can be found out. VCE is nothing but VCE plus VE. Similarly, using the double subscript notation, I'll write VBE as VB minus VE. I need to find out what is VB. VBE is a known value which is around 0.7 volts for silicon transistor. So VB is VBE plus VE. VE is calculated in the previous step here. So using double subscript notation, we can find out all the different node voltages. Let us quickly summarize what we did. First, we removed all the capacitors to isolate the AC signal sources. Then we applied KVL to the input side loop and found out what is the value of IB, which is equal to VCC minus VBE divided by RB plus 1 plus beta times RE. Then using the expression IC is equal to beta times IB and IE is equal to 1 plus beta times IB, we found out all the currents. Then by applying KVL to the output side loop, we found out what is the voltage across the device, that is VCE, which is equal to VCC minus IC times RC plus RE. This is by assuming IE to be almost equal to IC. Then static power dissipation PD can be calculated as this VCE into IC. Then all the node voltages were marked and VE was calculated as VE is the voltage drop across the emitter resistor RE. So VE will be equal to IE times RE. Then making use of double subscript notation, we can find out what are the node voltages VC and VB. So VC will be equal to VCE plus VE and VB is equal to VBE plus VE. This completes the DC analysis of emitter stabilized bias common emitter amplifier. Thank you.